Hey, what's up, guys? Yeah, so I want to make my own complexity theory. So today I want to talk about is NP and CONP and the factoring. So I will prove some complexity results about its factoring and also describe why people believe that the factoring is not NP complete. Okay, so please subscribe to my channel. So okay, so let me just write down the definition of factoring. Okay, I don't know why in the computer science that the deterministic language, usually people write that's the capital letter. Okay, so this is this. This is just the, let's say, give you a integer n. So this n is a n-bit number. Okay, and the written as an upper bound and lower bound. And this is true if there is this p such that p is prime. So let's say prime p such that p divides n and p is less greater or equal to L and less or equal to U. So this factoring is a decision language. So such that this is somebody give you N, L, and U, and you need to make sure you need to return one. So if you need to return one, if you can find a P such that P divides N, P is a prime factor of N, and P is between L and U. Okay, so this is the decision language, and there's also the factoring problem. Let me just call it factoring. So factoring is more general, right? So somebody give you n, so let's give you n. So given n, then you need to return the prime factor. So basically, you need to do a prime factorization. Okay, and any positive integer has a unique prime factorization up to the order, so up to the permutation, because the integer is a unique factorization domain. Okay, so you need to return n equals to, let's say, p1 r1, p2 r2, pn rn. Okay, and so usually in this a factoring search problem that we only require that you just output the p1. You just output all the distinct prime factor. Okay, so these are two factoring problems. Okay, and so first I want to show that they are actually related. Okay, so the first thing is I want to show is that if there is so this is the theorem. If there is a Turing machine, M such that M can solve, let's say M can solve the polynomial factoring. So let's say M can solve factoring in the poly n-time. Then there is another M prime, another Turing machine M prime. M prime can solve search problem, right? Can solve the small factoring in poly n-time. This is not difficult. The reason is very simple, right? Because let's say somebody gives you M, right? You can solve the effect. So all I need to do is just check, right? So let's just do let's do this, right? So suppose I can solve this factoring in the point in time, and I want to claim that there is a Turing machine that can solve this factoring in the point can solve the factoring, can solve the search problems. Okay, so idea is just using a binary search, right? So this is probably not difficult. Binary search. Okay, so idea is that somebody give you n, let's give it n, right? You first check that where the n is prime, so you can check whether n is prime or not. Okay, now you can check in the polynomial type because primary test is in n, and then you start from a lower and the upper to n. Okay, and if L less than U, then you just call let's say n L and U plus L divided by 2. Okay, and call this. Okay, so there is a two case. If you call this, then this is true. That means you find a prime factor, right? You find the prime factor, so you can just n divided by p1 and run the whole program again. right? I mean, if you get false, that means what? That means that I mean, if you sorry, probably this is not true, right? So if you know it's true, that means there's a prime factor that between L and U plus L divided by 2. Then you can just you can just do in L add 1, right? You can just L add 1. If you are not finding the answer, that you should go U minus 1. Okay. So if it false, sorry, you should add U to be how should I write it? So let me just clear the page. Sorry, I'm stupid. It's need a little bit long time. Whew. Because this is not my expertise. Okay, so if it's true, that means you've is a prime factor between here, right? So you can that U plus L divided by 2, given U, and otherwise that you did L equals to U plus L divided by 2. Okay, just maybe you can add 1. Add 1, right? Okay, so you can just keep using it, because if you give you 1, then if you give you 1, then you know there's a factor, otherwise it's 0. So you can just keep going it, right? And this is binary search, right? So you at most take log and times up to the middle error code, the up to the middle operation. And I already assume that the middle operation is around point n time, right? So it's poly, right? So it's still a poly. Okay. Okay, right. So this means that if you can solve the factoring the point in time, then you can solve the Turing machine and prime the point in time. Okay. And conversely, so conversely is so trivial, right? Conversely is that if one can solve, let's say factoring, that one can solve the searching problem factoring, then one can solve the deterministic version. Let's say I can solve this in poly n time. I can solve this in poly n time. Okay, so this is proof is almost trivial, right? Because let's say I first somebody give me n, and I first solve this. Right? I first using cofactoring oracle. So this factoring span point n time and give me all the prime factor. Let's say p1, p2, of the pn. And all I need to check is that I just check whether pi between L or and U. Okay, if I find it, if there is I such that this is true, then I output 1. Otherwise, that I output 0. So output 1. Otherwise, that I return 0. Okay, and then this also takes a polynomial time, because this n, actually the number of prime factor is actually bounded by log n. So this is you can prove this very simple. So the number of prime factor is bounded by log 2 of n, which is just n. Okay, so it's poly n. Okay, so you at most need poly n to check. Okay. Now let's talking about the complexity results. Okay, so now we know there are polynomial type related. And so I can make the factoring for given n, and the related only required to the decision problem. Because technically, when we say complexity class, then we are restricted to a decision problem. Okay, so theorem, which is very simple, is that the factoring is in NP. Okay, so this is almost trivial. Okay. Okay, so if you want to prove that somebody some decision language is in NP, all you need to do is find the witness. Okay, or basically define the verifier. Verifier. I don't know, maybe sorry, verifier. Okay, so you just need to find a verifier, and this is very simple, right? Because if X belongs to factoring, or if L belongs to factoring, that means there is a prime factor, right? So there's a prime factor P, which is in this region. Okay, so if I find if I find the weakness, then I can check this right, because I can first check P is prime. So this is in P, okay, and also I can check where P is this region. Okay, this also takes a polynomial time, right? Because it's very trivial. Okay, so everything is in polynomial time. Okay, so this is in NP. Okay, now maybe the hard part is to prove that this is a theorem that factoring is actually in CONP. Okay, so this is what maybe you need to think a little bit, because CONP means that if let's say this is L. Okay, so this just tell you that if X, so if you want to prove, so basically you want to prove the following. You want to prove that if X belongs to let's change the notation. If L belongs to this factoring, let's call this F. If F do not belongs to the factoring, then there is a weakness. So what is the weakness? Okay, so you should be able to verify the weakness and check that if you should first verify, oh, this is okay, this is actually the prime, and this is actually you can check the X do not. So if L do not belongs to F, then there should be some polynomial time checker that you can get it. You can immediately check X do not belongs to L. Okay. So idea is that so it's maybe not difficult, but one can think of the weakness just the prime factorization. Okay, so answer will be the prime factorization. So it's a prime factorization of n. Okay, so idea is that that you just take, let's say P1, P2 up to Pn is the weakness. Okay, so you can check that the Pi is in P. Pi is prime. So this will take the polynomial time, and then this n is bounded by log n, right? So it's still polynomial time. And you can check. Where Pi is in L and U. Okay, for every I. Okay, so if you don't find anything, right, then you just return false. Okay, so that means that factoring is CONP, right? If this answer do not belongs to F, then I can check that where there is a Pi, right? If it pass all tests, if not, if no any I in this region, then I just return 1. Then just return the I should return 1. Okay. So if L do not belongs to F, then I get it. Then I should be able to check this in the polynomial time. Okay, so these two give you factoring is in NP, and also factoring is in CONP by using the prime factorization and also the simple weakness. So just this one is just take the prime P, and then the other is somebody give you the prime factorization, then you can easily check that whether you can easily use this to check factoring is actually in CONP. Okay, so the result is this, right? So basically you get results looks like this. So which should tell you that the factoring it actually belongs to NP intersection with CONP. Okay, so this is why people do not believe that the factoring is NP complete. Okay, so this is a theorem, that the final theorem is true. I want to prove. So if factoring is NP complete, then the NP equals to CONP. Well, basically one can say that the polynomial hierarchy collapse into second level. Okay. Second level or first level? But basically, you know that polynomial hierarchy will collapse, right? Because if NP equals to CONP, then all the sigma 2 and the pi 2 will be all the same. And usually, I think most of computer science believe that all the class in the polynomial hierarchy are different from each other. Okay, so this is why people do not people do not believe that factoring is NP complete. Okay, the proof is very simple. Proof this is very simple, right? The reason is that let's first prove that NP is a subset of CONP. And the reason is that let's say you choose L to be an NP language, and you know that the NP factoring is NP complete, or let's call it F. Okay, so you can find a polynomial reduction such that you can find polynomial reduction to F. Okay. Okay, and which this you just take a negation, which you prove this. Okay. But what? But you know, right? But you know that the since F is in NP, is NPC, is in NP, right? Which tell you that the complement is in CONP. Okay, so which tell you that this guy is actually what? This guy is actually this. Oh, sorry. Let me just write this. Right, so F belongs to NP, F complement belongs to CONP, and also since F is also belongs to CONP, which tell you that F is also belongs to NP. Okay. Sorry, F bar is negation is belongs to NP. So this means that L bar is polynomial reduction to NP. Sorry, CONP. Just use this. Okay. So which tell you what? So which you prove that any NP problem is a subset of CONP, right? Because L belongs to NP, then L can polynomial reduction F. Then L negation is polynomial reduction F to F negation, and then the F negation is belongs to CONP by this construction. Okay, but then you prove that then you just take a complement. I mean, you can change this to NP, and you take the complements. You get L polynomial reduction to CONP. I mean, I can put NP here, right? Because F bar is basically CONP or NP. So if I put NP here, I think I can call both sides. I get L is polynomial reduction to CONP, which will prove that NP is a subset of CONP. Okay, and then vice versa. Okay, so now you prove that NP is a subset of CONP, and CONP is a subset of NP. So basically, you prove that NP equals CONP. So this is why factoring people do not believe that they're factoring NP. I think this is made polynomial hierarchy collapse into the first level, because the first level it should be NP and CONP. Okay, and then there is another theorem that if graph isomorphism is NP complete, then you can prove that the polynomial hierarchy will also collapse into a second level. So this is why this polynomial hierarchy statement is very actually really interesting. Okay, so I think this is my short note introduction for this NP, CONP, and factoring. See you guys next videos.